Lovely. So, good morning, J Prime. Make some noise. Yes. How was the traffic jam today? The metro was working, I guess. Yes, anyway, really good to see you here. And I hope you're enjoying. This is the hardest talk for the conference, day 2 in the morning.
Yeah.
Yes.
Everybody's still drunk, I guess.
Everybody is drunk, especially the speakers, after yesterday. Yes, and what we usually say, good morning, but today we say it a little bit differently. We say Gunnar Morling, J Prime. Yes, because Gunnar is here today, and well, actually, he's one of the most important specialists in data. Yes, don't hesitate. One of the coolest guys about data processing, about CDC, actually inventor of the CDC. Let's be honest.
Okay.
Yes, and really awesome and good pleasure to have him here. By the way, after one J Professional. Who was at J Professionals with Gunnar Morning? Is there anyone?
I was there.
Yes.
That's like there's some.
Okay, then you will learn.
Two brave people.
Two brave people. Yes. So once again, Gunnar Morning, everybody, and please welcome our good friend Gunnar Morning.
All right. Thank you so much for the nice words. Well, welcome. I hope you're all awake. You had a good. Great first conference day, and I hope you will have another great second conference day. And I'm very happy to kick things off for you. Okay, so I mean, Dimitri shortly mentioned CDC, Change Data Capture, and I will explain what it is and why you would want to use this. And I've been working on this for, well, quite a few years now as part of what's called Debezium. It's an open source project for Change Data Capture, CDC for short, so I used to be the project lead. And, while doing this, there were certain themes which came up again and again. And one is this topic of today's talk, which is dual rights. And this is not a good thing. You want to avoid it, and I will explain you why. And this, kind of became a meme. At some point, we even did a T-shirt which says, "Friends don't let friends do dual rights." And the other day, I was cleaning up my wardrobe, found the T-shirt, and then I thought, hey, I should actually do a talk about this, And I realized I could have ironed the shirt, but, you get the gist of it. Okay. So, I want to talk about a couple of things. I want to talk about the Outbox pattern, which helps us to deal with this dual right problem. I will talk a little bit about how to implement the Outbox pattern, and we will discuss, some alternatives. Does it still make sense? Are there trade-offs? And so on. So that's the rough idea for the talk today. A few words about myself. I work at a company called Confluent. They were the original creators of Apache Kafka. By the way, who is using Apache Kafka? So, okay, this should be way more. So I would say that's maybe like 1/5 of you. I hope it's going to be like half of you next year. So yeah, at Confluent, I used to work, as I mentioned, at Debezium, and I'm involved with a few other things, and one of the things is the 1 billion row challenge. So who has heard about the 1 billion row challenge last year? It was a coding challenge, okay? Few people. Did anybody participate in the 1 billion row challenge? Like nobody? No awesome hackers who participate? Well, you should maybe participate next year, because I'm thinking to do it again. So this was, kind of like a viral challenge. People went all the way to tune their implementations, all kinds of big names from the Java community, like Thomas Wörtiger, who is the lead of GraalVM, Cliff Click, who was the original developer of the hotspot JVM. So all those people, were implementing on the challenge. And this happened last year. And then people asked, are you going to do it again this year? And I said, no, I'm not going to do it this year because I was still recovering. It was just too much work. But maybe I'm going to do it again next year. And that's why I'm mentioning this, because if you have some ideas what could be an interesting topic for a coding challenge, let me know. And maybe we can talk about it and get something started for next January. All right. Okay, so let's get into it. So let's get into this dual rights and Outbox pattern stuff. So the idea is, well, I guess many of you work on enterprise systems, right? So maybe order management systems or whatever it is really, right? And you may have a microservices architecture, which means your overall domain, your problem space is decomposed into multiple systems, which of course interact with each other, right? And very often what you have there is you need to modify the state in your own services database. So let's say a purchase order comes in, your microservice, it needs to persist that purchase order in its own local database. And now, well, this is a microservices system. It's a connected system of services. Of course, we want to loosely couple them, and we don't want them to rely on each other, but at the same time, they don't exist in isolation. So they will need to cooperate and collaborate, and this means our first microservice, very likely, it will need to notify those other services about this new purchase order. And now those two things, like persisting a purchase order in our own database, and then telling those other services about this fact, this needs to happen consistently, right? This needs to happen in particular atomically. So we either want to do both of those things or none. We don't want to update our own database, but then fail to tell the other services. So that's the challenge. And well, what could we do to solve this? And this is exactly where now this idea of dual rights comes in. Because, well, this is how things could look like, right? So we have our order service. Maybe it has a REST API. It receives requests to place new purchase orders, and, well, it will store them in its own database, right? So maybe Postgres, MySQL, you name it. And at the same time, we want to notify those other services, like our shipment service, order has been placed, so we need to create a shipment, or we want to notify our customer service that, credit balance needs to be deducted, and so on. Very often, you want to put something like Apache Kafka in between those services, so they don't rely on each other synchronously. So this is something you might find. Maybe you're even doing this in production right now. The problem there with this is, this looks fine on the surface, but well, now those two things, they're actually not guaranteed to happen transactionally or consistently. So, for instance, it could happen, we write to our database, commit a transaction in our, let's say, Postgres database, then we want to send a notification via Kafka to those other services, but now this failed for whatever reason. Maybe our Kafka cluster, is down, or we cannot reach it, there's a network split, so we are ending up in this situation where we have done one of the things, we have persisted our order, but we have forgotten or we have failed to notify those other services. And that's bad, right? Because now, well, we have a purchase order in our system, but it might not be fulfilled because, well, we didn't tell the shipment service. But that's sort of a problem, right? Also, there might be an ordering concern here. So let's say we do multiple changes shortly after another which apply to the same purchase order, let's say some updates, or to the same customer, and they happen shortly after another. What could happen is you apply those changes, let's say, A before B in your database, but then it could happen you actually send B before A via Kafka to those other services. So again, your overall system state would be inconsistent. So that's not something which we want to have, right? That's what you want to avoid. And now the problem is, again, it's very tempting to do this, and I've seen it again and again, and it looks fine. It might work fine for a while, right? But errors are guaranteed to happen. At some point, you will just run into the situation that this does not work, and then you have some trouble. Okay, so that's what we not want to do. And the question is, well, if we don't do that, what should we do instead? And this is exactly what this Outbox pattern is about. And this is what I want to dive into a little bit. Okay, so let's see. Well, I hope I could make the case, well, as things are, I cannot guarantee I update my database and I send a message to Kafka transactionally or consistently. It's not something as of today which I could do. So those two systems, they are not part of one transactional boundary, one distributed transaction, so I'm subject to those potential inconsistencies. But I always can update a single resource consistently, which in this case is my own database. So let's zoom in a little bit. Let's say I have, in my domain, I have tables like customers and addresses. And now if we receive that request, new purchase order comes in, I will be able to submit a transaction in my own local database. I guess that's pretty straightforward. And now what I do as part of the same transaction in this database, I also persist an event in another table which is called the Outbox table. And this Outbox table, this is now my messaging channel, let's say, to the outside world. All this happens locally within one database, one local transaction. So this happens atomically, right? So if this transaction commits, we are sure we have updated our customer and address table, and we also have inserted this event into this Outbox table. Or if this transaction rolls back, then we are sure that none of those writes have happened. So this is atomically, it's also like, if like all the ACID transactions you would expect from a transaction. Of course, now the question is, well, persisting a message in an Outbox table, that's interesting, but how do we get it from there to our consumers? And this is exactly where a component gets added, which is called the Outbox relay. And we will dive into different implementation approaches for that. But the Outbox relay, that's in charge of extracting the messages from this Outbox table and, well, send them out to our consumers. There could be different ways. Many times, or oftentimes, this is done via a system like Kafka. So the Outbox relay will grab all the messages from the Outbox table and send them to Kafka. And now this avoids this dual write issue because, well, we only have written to our database. So as I mentioned, this happens transactionally. And this Outbox relay, well, if there is something in this Outbox table, it will be able to extract that change and propagate it to our consumers. And typically, this happens with what's called at least once semantics. So this means, this Outbox relay, it might get messages from the Outbox table, but let's say it crashes. At some point, it will be restarted, and it might happen to extract a few messages which it already got before a second time. So consumers, typically, they would have to expect to see duplicates, but we will see how we can handle this. But it's not a big problem in reality. So this addresses the concern of dual writes, consistency, and it also addresses this ordering concern, because as we will see, the messages in this Outbox table, they exactly also represent the order of how we transactionally updated our own database. So also the ordering concern is addressed. Okay, so that's still, let's dive more into the details. So I mentioned, okay, we have this Outbox table. We will persist outgoing messages there. So how does this table look like? And most importantly, there is what's called, or what you could call, a payload column. So this really is the message which you want to send to external consumers. And this could be really anything. So here, for the sake of the example, I put some JSON structure, as per our domain. So it would have all the data fields which you want to emit. But it also could be something like Avro or protocol buffers. Really, whatever works for you, what are you using in your stack, you could use this as the format in this payload column. That's the most important thing. And you could leave it at that. So that's the one thing which you need to have. But then there's a few other data items which you typically also want to store in such an Outbox table. One of them is, and I'm using here the terminology of the domain-driven design. I guess many of you are using that. So you want to have something like an aggregate type, so which defines, okay, what is the kind of entity or aggregate object which is represented by a given object or a message in this case. So you could have something like purchase order, or customer, or whatever your domain is about. And the idea here as well, those aggregate types, we could use them to fan out different Outbox events of different kinds, for instance, to different Kafka topics. So that if you have a consumer who's only interested in purchase order events, it would be able to do so. So that's the aggregate type. Then we also want to have something like an aggregate ID. So that's the ID of our purchase order or the ID of our customer. And this is important to ensure ordering because, well, typically we don't need global ordering here. So we don't need, to ensure the ordering is consistent across all our purchase orders or all our customers. But what we do want to ensure is that the events for a particular aggregate, that they are correctly ordered. So all the events which we emit, let's say for purchase order 1, 2, 3, they should be received by consumer exactly in the same order as we have created them. And this aggregate ID, so those of you who are familiar with Kafka, I guess you will see where this is going. This will be used as the Kafka message key because this ensures that all those messages with that ID will go into one partition in our Kafka topic. So that's the aggregate ID. And finally, well, we want to have something like an ID probably, so we can uniquely identify our events, for instance, for deduplication purposes. Let's say, we get a duplicate. I mentioned this probably has at least once semantics. So a consumer could then use that ID to see, okay, I have seen this event before, and if I get it a second time, I probably will just put it aside and ignore it. Okay. So all this is still on the high level, right? So we have an Outbox relay, we have an Outbox table, and well, we can use this to get our messages from our application to our external consumers. Now the question is, how can we actually do this? And how can we implement this Outbox relay? So let's dive a little bit into that. And there's two different approaches which I want to talk about. And the first one is polling. So essentially, it's, I guess, pretty intuitive. So we would go to our table, to our Outbox table, and then we would query, are there new events in that Outbox table? So for that, what we would need is we need to have some sort of ordering field, right? So yeah, like a position, you could call it, right? And then essentially our query in the Outbox relay, it could select all the Outbox messages which have a position which is larger than the last one which we fetched before. And we will order it, of course, by position. I guess that makes sense, right? So we essentially go through that Outbox table ordered by this position. And again, and there's so many cases where those things seem to work fine, they seem to be a good idea on the surface, but actually the devil really is in the detail, because there is some problems with that. But first of all, let's look at the happy part. So this is, how this might work actually. So let's say we use a database sequence to produce those position fields. Well, we could have 3 transactions. In each transaction, we retrieve value from the sequence 1, 2, 3, and we insert them. Once the transactions commit, we insert them in that order into that Outbox table. And if our Outbox relay fetches the records from the table, we will have the correct ordering. So far, so good. But what happens now in a situation like this? So let's say we have those 2 transactions, 1 and 2. They happen, concurrently at the same time. And now the problem is, if we retrieve values from a database sequence, we could end up in a situation like this. So we have our transaction 2, which first fetches value from the sequence, so we get position 1. And then later on, while this transaction still is running, transaction 1 also fetches a value from the sequence and gets, of course, value 2. Now this transaction 1 commits before the transaction 2. So if you look at our Outbox table, and if we query it ordered by this position value, well, suddenly we would get the event which got emitted by transaction 2, we would get that before the one which committed later, which of course is not what we want, right? So our messages would be incorrectly ordered. So that's a problem. But there's even a bigger problem. We also might actually miss events. So let's look at this kind of situation. Again, we have like 3 transactions. They insert values in this Outbox table. And let's say we poll in our Outbox relay 1 one time, and only we see the first message. So we insert this message into our Outbox table. That's good. And now we poll again where this red line in the timeline is. So at this point in time, transaction 3 has committed already, while transaction 2 still is running. So we run our query, and message or position 1 had been the previous one, which we polled. So we say, please give us all Outbox messages where the position is greater than 1. And now, at this point in time, only transaction 3 has committed. Well, we would get this message with ID 3 or position 3, right? And we would insert that. And later on, transaction 2 commits. But at this point, we already have advanced to position 3. So we would ask, now give us please all messages with a position greater than 3. So we would essentially miss this Outbox event which has been persisted by transaction 2, which of course is a problem, but because we wouldn't have all the data propagated. Now, there's one way where you can avoid this, or how you could avoid this, which depends a little bit on the database. So essentially, for instance, what you can do with Postgres, you could say, I only want to get data from those transactions where there is no other pending transaction which has started before. So essentially, again, if we are at this red line, we could query in a way that we wouldn't get the third event before this transaction 2 has committed. So, there's ways for dealing with it, but it also means if you have like long-running transactions, which potentially might be completely unrelated, they would essentially block you from advancing with this Outbox table. So again, it's not ideal. So really, the devil is in the details with that. Okay. And again, I'm not even saying you should never do this, but you should just be aware of all the implications, all those details, and you should think about, okay, is this, how can I deal with that? But I'm not dismissing it. Now, there is, I would say, a much better way still. And I would say whenever you can use what's called log-based change data capture, this is what you should be doing. So let's take a closer look at that one. So the idea here is, well, instead of going to our database and querying this table for changes and trying to order it and having all those complexities, well, what if instead we could be notified by the database whenever a new event has appended to the transaction log? So I'm sure everybody who works with databases, you're all familiar or you're aware that all the databases they have what's called a transaction log, where all the transactions are appended one by one. And this transaction log, that's the canonical source of changes in our database, right? And the idea for log-based CDC, log-based change data capture is, well, we will extract all the changes from that transaction log, and this will be our source of information. And this is exactly what Debezium does. It's an open source tool for log-based change data capture. And again, it solves all those concerns. Well, we have a complete data view because, well, the transaction log in our database, let's say the bin log in MySQL or the val, the write-ahead log in Postgres, this is, that's the source of truth. It has all the data, right? So if we go there, we will be sure we have a complete view of our data, and also it guarantees the ordering because the transaction log, well, that's an ordered sequence of the changes which were applied in the database. So if we get there, we have the complete and correct data in the correct order. Now, how would you go and do this? How would you go to a transaction log and extract changes from it? Well, that's actually quite tricky. It depends, it differs between databases. There's different APIs, different formats, different ways for doing that. But the good news is Debezium, as an open source project, it deals with all that complexity. So, it has implemented those log-based CDC connectors for all kinds of databases like Postgres, MySQL, Oracle, SQL Server, MongoDB, many more. And then it emits one canonical change event format, which we will see in a bit. So it gets, it gives you a generic representation of database change events. That's it on a high level. So by the way, who is using Debezium in production? Oh, there's like a handful of you. Okay, that's the brave corner over there. Very good. Now, there's so many things, I could mention, I could talk about Debezium in terms of features. I don't want to spend too much time on it. There's this notion of snapshotting, where essentially we will start to bootstrap a new connector by just taking a fresh initial snapshot of our data. There's what's called message transformations, which you can use to modify your messages, now also using WASM, for instance. So lots of good stuff. But one thing I do want to mention is a change to the governance of that project, because initially, it always was an open source project available under the Apache v2 license, so very liberally licensed, but it was managed and run by Red Hat. So I also used to work for Red Hat while I was the project lead for that, and they owned the domain, they owned the trademark and everything, so they kind of controlled it. Still very successful open source project, lots of other contributors, hundreds of people have contributed, but still sometimes people have maybe they're a bit shy to contribute to a project if it's not living at a more neutral place, like an open source foundation, let's say the Apache Software Foundation, Linux Foundation, all those places, right? So then people are very willing to come together and contribute to one project, work together on one project, and there's not a single entity who is exclusively in charge. And this is also what happened to Debezium. Just very recently, it moved to what's called the Common House Foundation, which means now it has a vendor-neutral home. And there's, of course, still the people from Red Hat working on it, but then also other people, I hope, even more are now eager to come and join efforts to contribute to that project. Okay, so let's get back to the Outbox stuff. So what I want to mention is, I briefly spoke about those change events, and we see them here on the left-hand side. So this is how a change event, which you would get from Debezium, would look like. So the important thing to understand here, first of all, as well, this Outbox table, this is really only, it's also like an append-only log, right? So we will ever only insert into that table. We will never update events. If you think about it, it just doesn't make sense, right? So once you have sent a message, it's immutable. You don't want to update it, so it's always inserts. And this is on the left-hand side how it would look like. So you have, in this case, because it's an insert event, you have this after structure, which has essentially all those columns I mentioned before, right? So aggregate ID, payload, aggregate type, and so on. There's a bit more metadata, like what's the operation type. So this was an insert event, a create event. There's a timestamp, and so on. And the Kafka message key, by default in Debezium, that's the primary key of our tables. So that would be the unique message ID, essentially. So this is how Debezium, by default, would emit the events which we write to this Outbox table. Now, from a consumer perspective, that's workable, but it's a bit inconvenient. We rather would want to have a structure as we see it on the right-hand side. So essentially, we would want to have our aggregate ID as the Kafka message key, and we also essentially only want to have this payload as the sole message value in our Kafka messages. And also in particular, we don't want to have all the messages on a single topic, but rather we would want them to be split up by aggregate type. So in this case, it would be on a topic which only has order events. And there's a message transformation in Debezium, which we can see here, which you can apply to your Outbox table, and then it will on the fly transform those messages from the default representation into this one, which we can see here. So this is how you could very easily implement the Outbox pattern in Debezium. So let's think about a few more implementation concerns. So first of all, there's housekeeping. As I mentioned, well, the Outbox table, it's like an append-only log. So we go there and write new Outbox events. Of course, we also need to delete them, right? We don't want to have an ever-growing table. What could we do? Well, we could think about some sort of batch job which deletes Outbox events after some time, but actually we don't have to. It can be much easier, because what we can do is we can just, as part of our transaction where we insert events in the Outbox table, we also can delete them right away. And this might be a bit counterintuitive at first, but the idea is, well, this transaction, it will append those events, insert and delete, to the transaction log. Which means this is all we need for Debezium to be able to get the events from the transaction log. Now, if we ever go to our Outbox table in the database and we would do a select from, we would never see any events because, well, we always deleted the stuff right away. But still, we can capture those inserts from this Outbox table. And it also means we don't have to think about housekeeping, which I think is pretty convenient. Now, I guess, well, my favorite database really is Postgres, I guess, because it's so powerful. And as it turns out, for Postgres in particular, there is an even more elegant way for implementing that, because, well, we don't even need an Outbox pattern, an Outbox table in the first place, because what Postgres gives us is this function pg logical emit message. And this is a bespoke function which allows you to write contents, arbitrary contents, into the database transaction log. Now, what you write here, this will never show up in any table. It will exclusively exist as an event in the Outbox, in the transaction log. And this function, it has a couple of parameters. So this first one, this true, it says this is a transactional message, which means this write should only happen if our transaction commits. Then there's sort of like a type discriminator. So here we could say, okay, those are, those events in the transaction log, they represent Outbox messages. But we also, we could say those are purchase order messages, for instance. Then there is the payload, which would be our custom structure which we want to write. And this, I really like that because, well, it makes it even easier because now we don't even need to think about a table. Again, we don't need to think about housekeeping, well, because the database will just itself discard outdated transaction log segments. So if you're on Postgres, this is what I would recommend you to implement this. Okay, let's discuss some more implementation concerns. And one of them is in particular important, which is about backfills. So let's say, or snapshotting. Let's say, maybe we have an application which exists already, which has been running in production for quite a while, and now we are about to introduce the Outbox pattern to our application. Because maybe a new requirement came up, and we want to add this to an existing application. In this situation, what will happen is, well, we don't have Outbox events which correspond to the existing data in our database, right? So we need to bootstrap this state for our Outbox table based on the data which already exists. And well, how could we do this? Well, first of all, it could look like this. So our service, it nicely works. So it produces its regular Outbox events, persists them in the Outbox table. And now we could add a backfill process or feature in our application, which is in charge of producing those Outbox events for data which already existed in the database when we started to use the Outbox param. And now the challenge is, well, those two things happen at the same time, right? So our application produces regular Outbox events as data gets produced or updated, and at the same time, this backfill process also inserts Outbox events for already existing data. So it's sort of a data race, and in particular, we want to make sure that we don't override any Outbox events which our current functionality inserts by Outbox events from this backfill process, right? So we want to make sure that essentially whatever happens in terms of changes right now, that this gets precedence, essentially. And for doing that, so for resolving those conflicts, this is what we could do. Essentially, we could insert marker events in our Outbox tables. So we could say, we could employ sort of a windowed processing, and we could say, okay, we insert a start marker event and we insert an end marker event, and then between those marker events we insert our backfill Outbox events. And essentially those marker events, start and end, they give us a windowed representation of this Outbox table and the changes. And now we can essentially implement some sort of deduplication logic, which allows us to essentially make sure, whenever an Outbox event actually has been regularly produced by our application, we will take that instead of a backfill event for the same purchase order. And only we will propagate those backfill events for any data within that window where we didn't see a Outbox event otherwise. So I realized it's quite a bit to digest, but I want to mention it because it's a very powerful feature. And for those of you who are using Debezium, it might actually sound familiar if you have been using what's called incremental snapshotting in Debezium. And all this is based on a research paper which some very smart guys at Netflix wrote a couple of years ago. It's called dblog, a watermark-based change data capture framework, where they presented or introduced this chunking based approach which I just described. So I very much recommend to read this paper. It's very well readable, and this also is implemented in Debezium. Okay, so let's talk about item potency really quick. As I mentioned, we have at least once semantics here. So consumers might receive an Outbox event a second time. And the question is, well, what do they do about it? They somehow need to recognize it. So we could have a unique value, as we saw on the examples before, so like a UUID, and this would work. The problem is a consumer now would have to keep track of all the UUIDs which it ever has seen, right? So it would have to store all the UUIDs, and then when a new message comes in, it could go there, and it could check, have I seen this UUID before? And if so, well, then I will discard this incoming duplicate. So we have sort of an unbounded state growth. I mean, I guess at some point we could try and discard old UUIDs, but when would we be able to do so? So that's tricky. So a more elegant way would be to have a value which is guaranteed to monotonically increase. Because then we only have to store the latest value we have seen. So we could store that value, and then if we receive messages and they have a item potency key which is lower than that one, then we know, okay, we must have seen this before because, well, this value is guaranteed to increase, right? So that's much easier because we only have to persist a single value. The question is, how do we obtain such a monotonically increasing value? Because as I explained earlier, we cannot use a database sequence because this is not guaranteed to actually be monotonically increasing in the presence of concurrent transactions. But then again, going to the specifics of our database, we can find actually values which help us with that. So in case of Postgres, there's what's called the LSN, the log sequence number. And now this is part of all the events which we get from the transaction log. And Postgres guarantees to us that this LSN is increasing in commit order, which means it is monotonically increasing for our purposes, which means consumers only need to store the latest, the greatest LSN value they've ever seen, and then if they get events which are smaller LSN, they will know this must be a duplicate. But you can't use a database sequence. That's the most important thing. All right, so let's discuss this a little bit. I hope I could make the case, why is this useful? How can we implement it? But you also might have some questions. And some questions I see or I hear are, does this not increase the database overhead? Because, well, we persist now more data in our database, right? And I would say, well, it depends. So yes, but. So typically, this concern about overhead, it comes in two flavors. So there are two aspects to it. So the one is, well, we increase the size of our database because, well, we have more data which we store, for instance, in this Outbox table. Now, I would say this typically is not a concern because the data in this Outbox table is very short-lived. In particular, if you do what I showed with this PG logical emit message, well, this is just part of the transaction log, and this will be discarded very quickly, essentially as soon as this has been consumed by Debezium or our replication consumers. So yes, there is a little bit of more data which we write to the database, but it's short-lived, so I don't think it really matters. And the other concern about overhead as well, our transaction size gets bigger, right? Because as part of our transactions, we do our other writes. We write to our purchase order table, customer table, and so on. But then at the same time, we also write to this Outbox table, so our transaction size gets a bit bigger. And yes, that's true, but then I would say, typically that's not that's relevant really, because, well, there's a baseline overhead for running a transaction to begin with. We will do other changes already, and then typically if we just do another insert in a transaction where we already do 5 or 10 or whatever other database operations, it doesn't really matter that much. So I think this is more a theoretical concern. I've not really seen this to be actually a problem. The other one is, well, does this not increase the end-to-end latency? So instead of sending a message directly through Kafka, here we go through our database, then we need to have this Outbox relay, and then we send it to Kafka. Do we have a larger latency? And again, I would say, yes, on the surface it's true, but I would also argue it's not really a problem, because first of all, this log-based TDC approach, which I've shown with Debezium, this can be really fast. So typically, Debezium will capture events from a Postgres database within milliseconds. So you will have your data in 2-digit milliseconds, typically in Kafka. And then, of course, it depends on where you put it, but I've seen end-to-end latencies for data pipelines, let's say from Postgres or MySQL to something like BigQuery in a second or 2 seconds. So, latency is really low. And also, I would say, well, this is a loosely composed system of microservices, right? So I would argue this shouldn't matter that much anyway. So if we are in a situation where we have a problem if our message from our purchase order service does not get to our shipment service within half a second, then I would argue something is wrong with how we have decomposed the functionality, right? This sounds like then we have too tight of a coupling. So again, yes, latency is slightly increased potentially, but in practice, it shouldn't really matter. So finally, I want to talk a little bit about alternatives. So maybe you wonder, okay, this all sounds good, but I feel this is too complicated, or can we not think about it in different ways? And I want to briefly talk about a few potential alternatives and the trade-offs which they make. So the first one would be, well, what I've shown you is, okay, instead of writing to those two systems, I've made the case we cannot do this reliably. I write to my database, and then from there we take the data into Kafka. You could have the idea, well, I could also do it the other way around. I could, do my write first to Kafka, and maybe if you're familiar with what's called event sourcing, this is pretty much what this is about. You could then consume those events yourself and put them into your own database so that you then can serve read requests of your own application from that database. And at the same time, you would send those events and you would have external consumers which could subscribe to the same topic. So this is something which you can do. I think it works fine in terms of overall consistency guarantees and so on. There's one big caveat with this. Well, writing through Kafka and reading from there. This is an asynchronous process, which means our service could write to Kafka new purchase order, and then the next second we go to our database and we query for the data, and it might not be there yet. So we don't have synchronous read your own writes. And this can be confusing to our users, because what could happen is, well, I'm in my e-commerce web shop, I place a purchase order, next second I go to the list of my purchase orders, and this doesn't show up. Because, well, it has been sent through Kafka, has not been put to this database yet, so our order list doesn't show my recent order yet. And for me as a user, that's very confusing, right? Because, well, has it been lost? Do I need to place it again? And again, there's ways you can deal with that. I won't dive into the details, but I would say, it adds much more complexity on an application development level than doing the other way around. So if we go to our database, we have synchronous read your own writes, right? So if a transaction has committed, the next second I go, or right after that, I can go and query the data, and it will be there. So I think it's just easier, consistent semantically. But again, it could be an option. The other one is, well, I made the case so much for, well, we cannot transactionally write to a database and Kafka. And still, as of today, that's true. But there is work happening in the Kafka community. So there is what's called KIP 939, Kafka Improvement Proposal, which essentially aims at solving that. So they want to have support for two-phase commit transactions and make this part of Apache Kafka. I'm not 100% sure where this KIP is at. I think it's still work in progress. But let's say, once this functionality exists in Kafka, well, then this would actually be fine from a consistency perspective. So, then we could have a distributed transaction which allows us, to enlist Kafka, enlist our database in the transaction, and it would be applied with atomic guarantees. So either both writes happen or none of them happens. That's fine. But I would argue, again, there is a trade-off which you make, and this is, well, this by definition reduces the availability of your own system. Because now, for your order request, in order to succeed, we need to be able to do those two writes. So we need to be able to update our database, and also we need to write a message to Kafka. If one of those systems isn't available for whatever reason, well, we cannot satisfy that request. So, which just means our overall availability now it's lower than it is if we only depend on our database. So again, it could be, or at some point it will be an option, but there are some trade-offs. And finally, which maybe is like the most interesting option here, alternative, let's say, is, well, we also could use what's used stream processing. So who of you is using Apache Flink? So yeah, again, like a handful, 5 people. Okay, very good. And again, there could be an entire talk or an entire day of talks about stream processing in Apache Flink. But on a nutshell, on a very high level, what happens here as well, we could try to produce those Outbox events based on our actual table level change events. So in this case, we would use Debezium to capture the changes from our tables, like customers and addresses and purchase orders and so on. And by default, Debezium gives you a Kafka topic per table. So we would have a Kafka topic with customer change events, with address change events, with purchase order change events, and so on. And then we could use a tool like Apache Flink for taking all those streams, all those Kafka topics, and essentially merge and join them in an incrementally computed way. So just to give you an intuition how this could look like, there's different APIs in Flink. The one which I think is the most approachable probably is Flink SQL. So essentially, this allows you to use SQL to implement queries in a real-time fashion against streams of changes. So in this case, it could look like this. We could essentially join our two Kafka topics, purchase orders, with order lines. Maybe group it so we have like a single nested data structure for a particular purchase order, and then we could take this data and insert this one into another Kafka topic, and our consumers would subscribe to that. So, again, there's so much which could be said, but really on the surface, this is how you could do this, using a single Flink SQL streaming query for joining your table-level events. And then you wouldn't have to, modify your actual application, and it wouldn't have to do those Outbox writes. And this is in particular interesting. Well, maybe we have an application, a legacy system, and we cannot really modify it, or we don't want to modify it, and we don't want to add an Outbox table to it. So in that case, doing this sort of thing after the fact, this could be very worthwhile. Now, I guess you get already a feeling this also adds quite a bit of complexity, right? Because we need to add this stream processor into the mix. We need to operate and run it. There is questions around, transactionality. So maybe we only want to emit a result from this join once we have seen all the events from a single transaction. So quite a few things like that. So worthwhile option to keep in mind, but it brings in its complexities. All right, and yeah, we're pretty much on time. But to briefly summarize, I think the most important point I could make, or I hope I could make, is, well, all this is about trade-offs, right? So I'm not here to tell you, okay, this is the one way how you should solve a particular problem. There's the one best way. There are no silver bullets here, right? So you really need to think about your use cases, your specific requirements, the semantics you need, and then you need to use one of those options, one or the other. Definitely, if you can, so if you are in Postgres, I would say, use this function, PG logical emit message. Definitely, I think this makes things very easy. The most important thing is, just coming back to the beginning, don't do those dual writes, right? So this is really the one thing which you should not do. Just try and hope for the best. Writing to a database, writing to Kafka, hope is not a strategy, right? So this is bound to fail, so don't do that. Few resources, so if you want to connect, again, as I mentioned, I would love to hear from you about ideas for 1BRC, 1BRO challenge, but also if you want to talk about Debezium, Kafka, Flink, this is how you can find me. And with that, I would say thank you very much. Have a wonderful rest of the conference.